Hello everyone, today we will be exploring how the launch angle and initial height of a projectile affects its horizontal range and maximum height. Our aim is to find the optimal angle for both the longest range and maximum height. My hypothesis is that the horizontal range of a projectile will increase as the angle increases from 0 to 45 degrees, and then decrease as the angle goes below 45 degrees. The vertical range of a projectile will increase as the angle increases from 0 degrees to 90 degrees. For variables, controlled variable is going to be same method used for each trial. The initial velocity of water, which is going to be full open tap, and level height of the table. The independent variable is going to be the angle that the water is being shot at. Dependent variables include horizontal range and maximum height. For the method, this experiment uses a retort stand positioned on the table with a height of 0.93 meters, a 4-pronged clamp, and a pipe hose connected to a water supply are set up. The inclinometer is used to adjust the launch angle, while a camera records the water stream's path. The landing spots are marked with chalk to measure both horizontal range and maximum height. The experiment is conducted at launch angles of 0, 30, 45, 60, and 75, with 3 data sets stored for each angle to ensure accuracy. The angles were measured in the domain of 0 to 90 degrees. The time it takes for the water to hit the ground is also recorded using the camera, allowed for analysis of the projectile's flight duration. This setup can be seen in figures 1.1 to 1.6. For the results, it can be seen that in figure 2.1 there is a parabolic shape. At 0 degrees it has a range of 2 meters and increases to a maximum horizontal range at 30 to 40 degrees being 3.12 meters. Afterwards it falls down to a 1.26 meters at 75 degrees. Next, with figure 2.2, we can see that the maximum height is increasing each time the angle increases. This seems to be a proportional relationship with angle and distance. The hypothesis proposed that the horizontal range of a projectile increases as the launch angle increases from 0 to 45 degrees, then decreases as the angle exceeds 45 up to 90. However, this relationship changes when the projectile is launched from an initial height. For projectile launches from the ground level, 45 degrees is indeed considered the optimal launch angle for maximum range. However, in situations where the projectile has an initial height above the ground, the optimal angle for maximum range will typically be less than 45 degrees. This is due to the fact that the higher angle increases the projectile's time in the air, thus reducing the horizontal distance traveled. When launched from a height, the projectile spends more time rising before descending, and launching at too steep of an angle leads to longer flight times and smaller horizontal range. This can be seen in the collected data parabolic trend, with the overall pattern showing that the range increases to about 30 to 40 degree range, and then it begins to reduce till the range reaches 0 at 90 degrees in the domain of 0 to 90 degrees. As seen in figure 4, through the usage of figure 3's formula for initial velocity, the calculations for the formula for most optimal angle was derived. After applying the formula, the most optimal angle for horizontal range is 37 degrees, which is in our expected range. Changing the initial height changes the optimal angle, as we can see here. Horizontal velocity is constant, so whatever the initial velocity in the x-axis is, will be the final velocity. Hence, having a higher horizontal initial velocity by lowering launch angle, hence effectively reducing velocity for vertical height, will result in a larger horizontal range. This can be seen in the data below. The data shows a linear relationship between range and time for each launch angle, meaning that range and time are proportional to each other at all angles. This indicates that the projectile travels at a constant horizontal velocity during its flight, covering the same amount of horizontal distance for each unit of time. Now, it is to be noticed that even though the range and time are proportional for each angle because the relationship is linear, the rate at which range increases with time differs because the horizontal velocity is different for each launch angle. The gradient of the range versus time graphs represents the rate at which range changes with respect to time. In other words, it indicates the horizontal velocity of the projectile, as range is the product of horizontal velocity and time. Range is equal to Vx multiplied time. The higher the gradient or the slope of the values, the higher the horizontal range. This, however, is not always true, since range is not only just a horizontal, it is also vertical, which also has an effect. At 0 degrees, the projectile moves horizontally at maximum horizontal velocity, but it doesn't travel very far because it doesn't spend much time in the air, since it has no vertical motion. In contrast, at 37 degrees, the most optimal angle, while the horizontal velocity might not be the highest, the projectile stays in the air longer due to its vertical motion, which allows it to cover a greater horizontal distance over time, resulting in the maximum range. The second part of the hypothesis states the vertical range of a projectile would increase as the launch angle increases from 0 to 90 degrees in the domain of 0 to 90 degrees. This part of the hypothesis remains true as the launch angle increases, the projectile's vertical range increases. This is because as the angle increases, the vertical component of the initial velocity becomes larger, allowing the projectile to reach greater heights. At smaller angles, the projectile moves mainly horizontally with little to none vertical movement. As the range approaches 37 degrees in our case, the most optimal, the vertical and horizontal components balance, maximizing vertical range. Beyond 37 degrees, the vertical range continues to increase, but the horizontal range begins to decrease. It can be seen that the horizontal velocity is constant once it is shot, meaning it has a direct proportional relationship with time and the distance away from the starting location. On the other hand, gravity affects the vertical aspect of the projectile, causing a downwards acceleration of 9.8. This results in the vertical velocity decreases. This results in the vertical velocity decreasing as the projectile rises and increases as it falls, creating a parabolic trajectory. While the launch angle reaches 90 degrees, the projectile reaches its maximum height, the maximum height being 2.16 meters. Increasing the angle will not result in a higher maximum height. Instead, an arc in the opposite direction that mirrors its supplementary angle will form. For example, a projectile launched at 100 degrees follows the same path as one launched at 80 degrees, just in the opposite direction. This symmetry occurs because the vertical components of velocity behave identically for supplementary angles, leading to the same peak height but alternating the horizontal displacement. If we compare our results to the simulated and theoretically perfect data using the average of the initial velocity from the collected data, gives us 4.9 meters per second. We can see that both experimental and simulation results follow the same trend of increasing horizontal range until around 37 degrees before gradually decreasing. This aligns with the theoretical expectation that range is maximized near 37 degrees due to the initial height difference of 0.93 meters. Beyond this point, as launch angle increases, more of the initial velocity is directed upwards rather than forwards, reducing horizontal displacement. At 75 degrees, there is a sudden drop in range, which also corresponds to the highest vertical height, as most of the projectile's energy is directed in the vertical motion rather than horizontal. The experimental data closely follows the simulated results within the average error range of 2.54% across all three columns. Data also supports that as the angle increases, so does the vertical range, reaching maximum height at 90 degrees. The 14.52% error at 75 degrees is most likely due to the X-range measurements, easily having errors at step angles, meaning small inaccuracies in measurements have a larger impact. Additionally, Theoretical calculations often assume ideal conditions, such as no air resistance, but in the real world, factors such as small variation in launch angle or inconsistent pipe pressure, as well as air resistance, all have an effect. When the hose was positioned to a larger angle, the pipe would not give accurate water flow and reach such heights that air resistance greatly affected the flow of water, giving inconsistent results. Some real-world applications of the study of projectile motion include firework displays. The trajectory of firework shells are calculated to ensure they explode at the right height and distance from spectators. Similar to our experiment, engineers study how the launch angle influences maximum height and horizontal range of a firework, and how varying angles are used to achieve the perfect arc in the sky, producing a visually appealing explosion. Some other uses include forensic scientists using projectile motion principles to analyze the trajectory of bullets in crime scenes. By studying the angle and velocity of a bullet, they can deduce the shooter's position and reconstruct the events of the crime. This knowledge is crucial for solving shootings or accidents, providing valuable evidence for investigations and helping law enforcement understand the dynamics of violent incidents. The accuracy of the measurements was limited by the tools used, such as the inclinometer and the method of tracking the water's horizontal range. Inconsistent tap pressure and variable angles might have led to slight deviations from the ideal projectile motion predictions. To make sure all variables were constant, acceleration due to gravity was calculated to measure if the acceleration was constant or not, hence proving accuracy. Calculating the downwards acceleration proves the accuracy of the experiment by providing a way to verify the consistency of the data. The calculated values for acceleration remain close to the expected gravitational acceleration of negative 9.81 meters per second, showing the reliable accuracy of the results. The average acceleration was negative 9.67 using the error percentage formula, and the percentage is only 1.43 error range, increasing accuracy. The experiment was conducted with multiple trials for each launch angle, which helped ensure consistency in the data. However, external factors like slight variations in the water pressure due to the inconsistent tap flow could introduce consistencies. Performing the experiment on different days might have led to different environmental conditions, affecting the repeatability and consistency of the results too. This was evident when removing dataset 2 from the sample to improve overall results. Hence, having results from a secondary source simulation and comparing results with it improves the reliability of the experiment. This comparison helps ensure that the results are consistent with established data, which in turn supports the dependability and repeatability of our findings, even with external variables. Using reliable websites and resources also helps with the reliability of the overall results, as seen in this table. The experiment's validity is influenced by a few factors. While it generally follows the principle of projectile motion, air resistance was not accounted for, which reduces the overall validity. Conditions such as inconsistent water pressure, along with fluctuating environmental conditions such as temperature, air pressure, and wind, further affects the projectile's trajectory and reduce validity. Furthermore, the experiment was conducted over multiple days, and varying environmental conditions on such days might have led to slight differences in the range and height achieved by the water stream. This inconsistency in conditions further underdetermines the validity of the results. Despite these limitations, the general trend observed in the data, such as the increase and the decrease in ranges as the angle changes, are still within the expected behavior of a projectile, confirming that the core concept of projectile motion was observed. However, to fully validate the experiment, it would be important to control these external factors, such as using more precise water flow system and ensuring the experiment is conducted under consistent environmental conditions. To improve the accuracy, reliability, and validity of the experiment, the use of a more precise inclinometer for the launch angle could help eliminate small errors in angle measurement. Additionally, giving a constant water flow rate would ensure better results for each trial. Conducting the experiment in a more controlled environment, such as an indoor lab with consistent temperature and no air resistance, would help reduce the impact of environmental variables and would give more reliable data for higher angles. The resources used were very reliable and easily accessible whilst being relevant to the depth study.